Welcome, everyone. So today it's my pleasure to welcome Danielle Maddox Robinson. I'll be talking about physics-constrained machine learning for scientific computing. Yeah, thank you.
Great. Thank you so much for the introduction and for having me today. I'd like to discuss our research that started in my thesis from the Institute of Computational Mathematical Engineering at Stanford to our recent research at AWS AI Labs, which is investigating how can we use machine learning to speed up physical simulations and in particular incorporate techniques from numerical analysis. So to get started, I wanted to introduce our team as well as external collaborators that I've worked with on the papers I'll be discussing today, from my thesis advisor, Professor Margot Gerritsen, as well as Luis Sampaio, and our collaborators on this recent scientific machine learning work from our PhD student interns, as well as my Amazon coworkers, Shima and Gaurav, and Amazon scholars, Michael Mahoney, Christos Flautas, as well as Ru Wang and his PhD advisor, Rose Yu at UC San Diego. So today what I'd like to discuss is how we can incorporate techniques from numerical analysis into black box machine learning solvers to help with generalization, improving PDE and ODE solvers. So in the first part of our talk, I'll be discussing time series forecasting, which was a focus of our group at Amazon, in particular probabilistic time series forecasting, but in the case of continuous dynamics, with a particular application to COVID-19 forecasting. This was our work in 2020, which led to a Best Paper Award at the Machine Learning and Public Health NeurIPS workshop. And then I'll discuss our recent work and our paper, Learning Physical Models That Can Respect Conservation Laws, where we propose a framework, ProbConserve, for enforcing conservation laws within black box solvers. And in this work, we're trying to do this by incorporating the integral form from finite volume simulations. And the last physical constraint we'll look at today is enforcing boundary conditions in another common solution in scientific machine learning, black box neural operators, with our proposed Boone method in our ICLR paper this year. So to get started with the team's general time series forecasting definition, what we were trying to do is predict the future behavior of a time series. So we have ZIT, and we're given the measurements in the past up until some time, capital T, which is denoted by the green vertical line here. We're also giving access to features or covariance XT in the past as well as the future. Well, the problem definition is try to calculate the probability of the future values of the time series up to a forecast horizon tau, conditioned on its past values and the features in the past as well as the future. So the idea here in our DeepAR paper is that we can learn a probability distribution and then compute the sample paths from here. Another method that's in our GlueNTS library that I linked to below is MQCNN, which is more of a sequence-to-sequence structure where you do a type of quantile regression to learn the quantiles directly and output the P50 or P90 quantile, for instance. An advantage of using this probabilistic forecast is then they can be then used to make optimal downstream decisions by incorporating the probability to determine the best action. And what we'll see is in ProbConserve also for PDEs, incorporating this type of probabilistic uncertainty quantification does help in a downstream task such as shock location detection. I've linked below to our JMLR paper on the GlueNTS library. I will not be discussing too much detail on the time series models today, but in our recent AI stats paper, we do discuss that numerical issues or consistency issues can even happen with the quantile regression problem in MQCNN, where you can have quantile crossing of the P50 being higher than the P90 forecast, for instance. So numerics can come into this problem as well. But the first example I'd like to look at today is an ODE view of time series forecasting. So going back to my background, which is developing numerical methods for PDEs that I studied in my thesis at ACME at Stanford. So this was our first work into trying to bridge the gap between numerical methods and PDE and deep learning solvers for PDEs or ODEs. So this was with my PhD student intern, Ru Wang, and his advisor, Rose Yu from UC San Diego, joint work with Amazon SOM professor Christos Flautas, as well as my manager, Bernie Wang. And this was our paper, Bridging Physics-Based and Data-Driven Modeling for Learning Dynamical Systems. So let's think about Z and suppose that there is an underlying dynamical system or continuous dynamics where it can be described by this corresponding ODE for unknown F theta. Now, theta is going to be the unknown parameters in the ODE, which we're going to aim to learn in our auto ODE method. Z is our observed variables, which for COVID-19 forecasting, for example, this could be the number of infected, the number of observed removed, or the number of total death cases that we're trying to forecast. Now, you may also have unobserved variables, U, given by another ODE for unknown right-hand side function, G theta, where we're also trying to learn these parameters. So in the case of COVID-19, these could be the susceptible and exposed population. You're also going to be given initial conditions. So the task to summarize is given the time series from time 0 to capital T. We want to learn F theta and G theta to be able to output the time series in the future up until forecast horizon tau. So when we first attempted this problem, we wanted to be able to use the black box deep learning solvers that we had built in GloNTS for COVID-19 forecasting. But what we found is when we tried to apply this to dynamical systems, these models, not surprisingly, very much struggled with distribution shift. So we look at a case study on the Lochner-Volterra ODEs, which are used in modeling population dynamics. And the unknown parameter here is Ri as well as Ki, which is the carrying capacity for a population PJ. And we also look at the Fixu-Nagumo ODEs, which are used in neurology to model squid axon, where C is the unknown parameter that describes how Y is reciprocally related to X. So what we see is, and we just find interpolation, meaning that the parameters in the test set are within the distribution of the training set. We see that on the interpolation task, and here the parameters we're looking at are K and C for Lochner-Volterra and F and Fixu-Nagumo, as well as we vary the initial condition, P0 and X0. If we do the interpolation task for a sequence-to-sequence deep learning architecture, we see it can reconstruct the future trajectories quite well in this plot, and then for Fixu-Nagumo on the right with a fully connected neural network. However, if we do try extrapolation, where the parameter values have different distribution in the test set than in training set, we see it's very hard to reconstruct these future trajectories for these models. So the idea here is, can we incorporate any domain knowledge, in this case from epidemiology via an ODE, to help better learn this process? And that's exactly what we proposed in the auto ODE model for bridging physics-based and data-driven simulation. So first, we're going to discretize the governing ODE with RK4, Runge-Kutta-4, which is a fourth order time series method. In particular, this is where the numerics is coming into the scheme. So there's been a lot of work on this optimize then discretize versus discretize then optimize framework. In particular, the optimize then discretize neuro-ODE viewpoint has been shown to not actually learn the true underlying continuous dynamics, which was in a paper by Michael Mahoney's group on learning continuous models for continuous physics. In particular, they show different performance depending on which time stepping method you use, if you use RK4 or the simplest first order forward Euler discretization in this type of continuous net. And you can show, as you take the time step to 0, that when using forward Euler, it may not actually converge and has these issues with generalization. So it's been shown to perform better in practice is this discretize then optimize viewpoint, which is what we do here. So the idea is we're first going to discretize the equation using this 4-step RK4 to give us fourth order accuracy. We'll compute the 4 stages here at the corresponding time points. And then we're going to estimate these unknown ODE parameters by minimizing the loss function. And here we use mean squared error. In particular, in this forecasting task, we know the values of Z up until time T. So once we've estimated the parameters, then we just integrate with RK4 to compute the future trajectories. So this is a quite simple model that performs quite well actually on the COVID-19 forecasting task. So to summarize, you'll see the algorithm here. We initialize our unknown parameters randomly. As I said, we'll discretize the ODE using RK4 up until the known time point. And the idea is just to simply minimize this L2 loss function to get an estimate of the unknown parameters. And then once we have that, and once it's converged, we'll use RK4 to generate the final prediction. So what ODEs do we use for COVID-19 forecasting? We use the SU-EIR equations. You could also use more complex equations, but the idea here is that the observed states, Z, are denoted by the number of infected, the number of removed, which is recovered plus death cases, and the number of death cases here. So these are observed variables, and it's given by this coupled nonlinear system of ODEs. And our unknown parameters are going to be mu I is the incubation rate, sigma I is the incubation rate, mu I is the discovery rate, and gamma I here is the unknown recovery rate. And then on the left here, you'll see the unobserved state. So these are the number of susceptibles, the number of exposed, and the number of unknown cases. One of the key parameters here that we found in modeling this effectively is this beta I of t, which is the transmission rate. In particular, we propose using a piecewise linear transmission rate because this is an example of where you need to be able to handle distribution shift. The beta I parameter transmission rate greatly changed according to policy of whether there were mass mandates or school closures, for instance. So having flexibility in learning this parameter we saw had benefits. And then the total number of states of the total population is just given by the sum of these 5 states here. So to look at some of the results, we plot our solution with the corresponding confidence interval for auto ODE shown in red, and the fully connected prediction shown in purple here. And we see that we're better able to capture the true forecasted value within the confidence interval. This is looking at the number of infected, removed, and death cases in Massachusetts for this week in August in 2020. And we show that we're outperforming the best performing black box deep learning model by incorporating the underlying ODE from epidemiology into the model. And that's the same results. We do quite a large benchmarking study here as well. Here we're looking at the mean absolute error at different time points throughout the summer of 2020 in July, August, as well as September, and looking at the number of infected, removed, or deceased cases for a fully connected neural network, sequence to sequence, as well as more advanced architectures such as transformer, neural ODE, as I was mentioning, as well as GNN models, graph convolutional neural network, and graph attention neural network, and comparing it to SU-EIR with fixed parameters. And we show that we have improved performance here as well. So that was our first work in scientific machine learning in terms of ODEs. In the next part of this talk that I wanted to focus on is my passion, which is on partial differential equations. So how can we propose a framework for enforcing conservation laws, which is really fundamental in scientific applications in engineering as well as aerodynamics, for instance, is this conservation property that the finite volume method guarantees. So first, I'll start with the review of the generalized coarse medium equation that I studied in my thesis. And then in terms of finite volume average-based methods that we propose there and how we use those numerical methods within our newly proposed ProbConserve paper. So we look at this generalized coarse medium equation because it's interesting mathematically, and in terms of machine learning, it gives us a very strong control by varying this parameter K of U to range from easy to hard problems. So that's also something I feel like is needed in this field, is to have a good benchmarking framework to what are these simple, smooth PDEs to what we'll call harder or not nice PDEs like hyperbolic conservation laws that do have shocks or sharp corner solutions that are difficult for numerical methods to capture. It also provides a family of equations. What are common applications of this equation? The simplest case and the most common that you might be familiar with is the diffusion or heat equation. So in this case, this K of U parameter is a constant coefficient K. And when you get here, then the K will come out of the divergence operator and we'll have a Laplacian, which means that we have the heat equation. Solutions to this are strictly parabolic in nature and have an infinite speed of propagation. Can show that a Gaussian is also a solution. So this is a simple equation to solve that has quite nice and smooth behavior. What's interesting about this equation, which drew our interest in my thesis to it, is that it can actually be degenerate parabolic in the nonlinear case. So if we have a nonlinear K of U coefficient, where here it's equal to a monomial of the unknown density. So in the porous medium community, U denotes the density and K of U denotes the underlying pressure. It's also been studied in the heat transfer community for nonlinear heat radiation or thermal conductivity by Baron Black. So this has been a problem dating back to the 50s. But this nonlinearity for small values of K, which we'll see on the next slide, can cause a seemingly trivial extension of the heat equation, parabolic equation, to act hyperbolic in nature. So we'll look at that example as well as the Stefan problem, which we'll call a hard case, because here now K of U is nonlinear, but it also is a discontinuous function of U. In particular, this unknown pressure value has a critical value and you're given by the step function. So the Stefan problem has commonly been used in crystallization models with level step methods being applied there, as well as in foam models. So we were interested in looking at it for modeling foams in my thesis, and in particular, the numerical artifacts that came from it. So as I said, what is this peculiar world of degenerate parabolic equations? So if we look at where it's strictly parabolic, here we have another instance of this family called the variable coefficient problem for K of X. If I start with the initial condition on the left, you'll see that at a later state over time, it is smooth. But what happens if you simply just update this K of X to K of U? So here for the initial condition on the left, for the PME, where it's a nonlinear monomial of U, you'll see that we have this sharp front that starts to form. In particular, it has a sharp corner here with an infinite gradient point to separate the region with the fluid from the zero density region or this degenerate region. And this curve has a finite speed of propagation, meaning that it does not dissipate or smooth over time, which can form numerical challenges. So as I said, we can view this GPME as a parameterized family of equations. The simple case of the diffusion equation on the left here, you'll see that we start with a sinusoidal initial condition that is damped or smoothed over time. And this is the constant coefficient case for K is equal to 1. Now, what happens in the PME is what we saw on the prior slide. This front is moving to the right with a finite speed of propagation that does not dissipate. And this is for K of U is equal to U cubed, where M, the parameter that we're going to vary in the deep learning model, is set equal to 3. For this equation, for the larger values of M, the more sharper solutions you get as well. In particular, you can show that it's only smooth for the value of M is equal to 1. Then we go all the way to the hard case for the Stefan equation, where now we have a discontinuous and nonlinear coefficient K of U. And here you'll see we actually have a shock forming. And the shock is used in two-phase flows to model the interface between two different materials, which is also very important in computational fluid dynamics. And see that this also moves to the right and acts like a hyperbolic equation. So where is this degenerate parabolic behavior coming from? If we look back at our equation and then rewrite it in terms of K, and this is motivated by Vasquez, the porous medium equation book, you can see that you get this corresponding expression. In particular, for small values of K, this smooth Laplacian term is tended to 0 if we take K to 0. And you're left with this term, which is an iconal equation. And in our paper, we put specific conditions on C of K such that this holds. So that's where you start seeing this degeneracy for nonlinear and small values of K. So now to review finite volume methods, what we found on this equation in the degenerate parabolic case is that the arithmetic and harmonic averages behaved quite differently, with the harmonic averaging suffering from numerical artifacts that we'll see on the next slide of lagging and temporal oscillations that did not occur with arithmetic averaging. So first is a review of finite volume methods. What we do in finite volumes is we discretize our domain into n control volumes. And here I'm showing a cell-centered grid with cell-centered coordinate xi. We denote delta xi to be the distance between xi and xi plus 1. So this is a uniform Cartesian match. And we know the coefficient values at these specific x coordinates. So to calculate the flux, which is K of U grad U, we need to define it at this cell face, xi plus a half. And what's commonly done in the literature is to use that via averaging methods. So you'll see the harmonic average on the left, which was preferred in our reservoir simulation community, because if we have the interface between a permeable and impermeable material, it did not allow flow across it. You can see that if you set Ki plus 1 equal to 0 here, that this equation is going to be 0. However, with arithmetic averaging, it would allow leakage from a permeable to impermeable material. And one of the main foundations in finite volume, which is going to inspire Prob Conserve, is this conservation. So what finite volume does is it actually operates on the integral form, which we'll see more later, of the conservation law, meaning integrating this equation over the spatial domain and then using the divergence or Stokes theorem. Take the integral of the divergence, which we're going to be left with is the flux on the boundary. So finite volume does a type of local conservation where it's integrating this equation over each control volume, which ensures that the flux out of control volume I is equal to the flux in to control volume I plus 1, which is known as this flux continuity condition. Once you have local conservation, that also guarantees global conservation, so that no mass can be created or destroyed on the interior of the domain, and that's all governed by the inflow and outflow on the global domain boundary. So as I mentioned, we observed the scheme very similar with harmonic averaging, suffering these strange artifacts only in this degenerate parabolic case, which really drew our attention to this equation and how we could devise models to fix this. This was first reported by Lippenkov's group in a JCP paper in 2017. The first observed artifact is lagging, which means that the numerical interface moves too slowly. You'll see the exact solution given by the solid black curve here. And the arithmetic average is matching it pretty well. It's just a little diffusive or smooth at this location. But harmonic averaging is significantly behind and has a different solution profile. You can even show that it does not resolve or converge as you refine the grid. What we also looked at is these temporal plots. So instead of plotting the solution at a particular time point, here we're going to fix the x coordinate. Here we use x equals 0.12. Since the solution is self-similar, you can choose any x coordinate and plot it over time. What we observe with harmonic averaging is these temporal oscillations. In particular, they're different than the oscillations that are caused by numerical dispersion and hyperbolic conservation laws, since they're occurring in the temporal plots and not in the spatial plots. And what we show in the paper is that they're equal, the width of these is equal to delta x. So as you refine the grid, the oscillations become higher frequency and do not actually dissipate, which means that even using adaptive mesh refinement, or we experimented with DVD schemes in time, did not solve these artifacts. So what we proposed in our first JCP paper in 2018, why harmonic averaging itself is not to blame, is using a modified equation analysis approach. So in this case, we assume that K is a differentiable function of U. So we're thinking about the PME case. If we write down the standard finite volume discretization for forward in time, so forward Euler in time, and central in space discretization, you will get the following expression, where the only terms that are going to differ is which averaging scheme we use in this Ki plus a half. We define these to be the fluxes in and out of that control volume. So I'll leave most of the details for the paper, but the main derivation that you can show is that the truncation error for the harmonic average can be written in terms of that for the arithmetic average with this additional term that has a negative sign. And this term is shown to be a coefficient of second order of uxx, so the second derivative of u. In particular, it can add an anti-diffusive effect to the equation. That's one of its effects, and the other effect is an advective nature, which also affects the shock speed. So what we propose in this paper is the modified harmonic method, or MHM, which discretizes these terms and adds them back to the scheme with the opposite sign to counter effect the numerical artifact. So it's a Laxman-Droff type of approach. And that works well, as I said, if you assume K of U is differentiable with respect to U. But what about the Stefan problem, where now we cannot differentiate? So here we propose the shock-based averaging method. On this more challenging case, even schemes with arithmetic averaging and the newly proposed integral average, which incorporates the critical pressure value U star into the scheme, did suffer these numerical artifacts. So what we propose here is adapting the finite volume grid using this shock tracking approach. So the idea is, what if we add an additional control volume around the shock point, which is denoted by this red star here, delta x star. So then we define delta x star to be the distance between grid point xi to the shock point x star. And you can also define the corresponding distance here. If we have this, we can define the corresponding stencil exactly because the solution is monotonic. So the pressure values, permeability values to the left are given by Kmax and to the right by Kmin here. And this resolved the stencils. But one of the main things we showed is that we needed to be careful with the numerics and directly incorporate the shock position into the scheme to be able to satisfy the Rankine-Hugonian condition, which is in our second JCP paper below. So that was a review of the numerical methods. Now I want to switch gears to the machine learning side of our recent work in this past year at AWS AI Labs. So this is our learning physical models that can respect conservation law papers. And we have a preprint on arXiv. It's currently under review at ICML as well. So to review, we've been discussing numerical methods. What are the main benefits? Finite volume by using the integral form of the governing equation is guaranteed to be conservative, which is very important in scientific practice, practical applications. But some limitations of the numerical methods is they do not out of the box provide any uncertainty quantification. In particular, if you change the initial condition, if you have uncertainty in the initial condition, you need to rerun the whole simulation. And these simulations can be expensive because basically you show that as you take the number of grid points or control volumes to infinity, the error will decrease to zero. At least we can prove that on linear problems. So in higher dimensions, these simulations can become very expensive and require high performance computing. So need to be rerun for different initial conditions, as well as different PDE coefficients. And in general, these models are not resolution independent, meaning I need to rerun them for the different grid resolutions as well. So now what's been happening recently on this exciting scientific machine learning front? So in 2019, physics-informed neural networks were proposed by Razi et al., known as PINs. So what these methods do is they try to parameterize the solution to a PDE with a neural network. And they do this by adding the differential form of the PDE to the loss function as a soft constraint. However, there's been limitations of these methods. In particular, by adding the PDE as a soft constraint, we're trying to add the Lagrange dual, which does not guarantee that the constraint is satisfied exactly. So in particular, these models are not guaranteed to be conservative, as we'll show, and do not provide uncertainty quantification. However, they are resolution independent, and they are trying to guide the black box solvers by incorporating the PDEs in some way as a soft constraint. On the other end of the literature spectrum have been the data-driven neural operator solution from Li et al., as well as Gupta et al. For Fourier neural operators, as well as multi-wavelet neural operators. So these take a different approach than PINs. Rather than parameterize the solution with the neural network, they're trying to parameterize the solution mapping from either initial conditions to the solution or different PDE coefficients to the solution. So this is a purely data-driven approach. It's not incorporating the PDE directly. And in particular, it trains on simulation data. So it's a supervised learning approach where we assume we have access to either simulation data or the exact solution. Since it's data-driven, it's not guaranteed to be conservative. We'll look at these more detail in the last part of this talk in terms of boundary conditions. So even if it's satisfied in the training data, there's no guarantee that at inference time, these constraints will be satisfied. They also do not provide uncertainty quantification. But as I said, they do provide a very flexible infrastructure. Since we learned this solution mapping, we're able to easily do inference on different initial conditions, as well as different PDE parameters in the interpolation task. And they're resolution independent, which is also quite important in practice, meaning that we can train on a coarse grid and perform inference on a fine grid. Lastly, there's also been conservative ML models proposed by Laura Zana's group in oceanography and Buchler et al. So here they're trying to add architecture-wise a final layer and to solve a linear system to make sure that the output tensor is divergence-free, which will satisfy conservation. So these models do satisfy the physical constraints. And lastly, as I said in this paper, we propose ProgConserve, which I'll discuss now, which satisfy these desired characteristics. So to review, we're going to define the differentiable the differential form for PDE. And in particular, the differential form is going to be given by this MathCal F operator. So we're assuming this is our PDE, which is defined on the domain omega, with this corresponding initial condition at t is equal to 0. And here we're going to assume we have a Dirichlet boundary condition. So we're fixing the solution at the boundary to be given by this function g of dx. And our boundary is partial omega. And this is defined for all times greater than 0. In this work, we look at conservation laws because of their fundamental importance to satisfy conservation. And for a conservation law, the differentiable form has this specific form where we're solving for the unknown u, and f is our corresponding flux function. So what we proposed using, which was inspired by finite volume methods that I reviewed, was the integral form of the conservation law. So the idea here is if I take the differentiable form that has been more commonly used in scientific machine learning in PINs or in physics-informed neural operator, for instance, what we propose doing is exactly what's done in finite volume. So I'm going to integrate this equation over the spatial domain omega. And what happens to the second term is using the divergence theorem, it can be simply written as the flux along the domain boundary. And here we propose enforcing global conservation over the entire domain. I've also integrated in time. So what you get is if u represents the density for this example of porous medium, the integral of u is the corresponding mass, which should be conserved. And the expression or constraint for the integral of mass is going to be equal to the initial mass minus the change along the boundary of the fluxes. And in 1D, this simplifies quite nicely. If you think your boundary is defined to be x0 and xn, what we get is that this is just equal to the flux into the domain minus the flux out. Should be the only responsible change of mass in the system. And what we see is that we can write this as a linear constraint using this boundary flux linearity assumption. So what we assume is that using the Dirichlet boundary condition or Neumann, the in and out fluxes on the boundary only depend on t and not on u. We define this operator, which is our constraint, MathCal G, to be equal to this integral of the mass of u, which is equal to b of t, which is going to be known to the system, namely the change in fluxes on the boundaries. Now, this also can apply in higher dimensions rather than just having the change in flux in the x direction. We can approximate it by a sum over each dimension in x and y. And for example, with nonlinear constraints, we can also solve this using a nonlinear least squares problem. But in this work, we assume we have this linear constraint. And here are examples that we're going to study of the linear global conservation constraint below. And so the first we look at is our favorite family of equations, the GPME, ranging from easy, medium to hard difficulty with the diffusion equation, PME, and Stefan problem. And these are the initial conditions and boundary conditions that we study, as well as the corresponding constraint value, which is governed by the change in flux on the boundary. We also show that our method does work directly on hyperbolic conservation laws by testing on linear diffraction as well as Berger's equation. So now let's define the ProbConserve algorithm. So the main idea here is that we can take a black box probabilistic deep learning model and train it via a supervised loss function. And the main idea is that it just needs to output a mean and variance estimate. And then we apply our constraint using the integral form to adjust the corresponding mean and covariance. And so the exact input is going to be the constraint matrix G. And this is the discretization of the continuous integral. And what we show is that you use higher order discretizations or a bit more careful with the discretizations, you also get higher order accuracy, which is shown in ProbConserve with diffusion, for instance, on the PME for sharp values. We also input the corresponding constraint value B and this noise sigma G. So what is the noise term? We propose a probabilistic framework to enforce this constraint. As you see below, we set B is equal to GU plus sigma G epsilon, where epsilon is normally distributed. And we'll show that we actually have a theorem that this probabilistic framework gives us uncertainty quantification, and it also, more importantly, gives us strong control on the conservation constraint if we want to enforce it exactly, or a bit looser tolerance here through this sigma parameter with theoretical guarantees. And then you also give the corresponding input points of this where you want to output the solution on the output grid. So this is a type of interpolation task. Examples of this step one black box model F beta could be Gaussian processes, Or what we look at in the empirical section is an attentive neural process by Kim et al. In 2019. And what do is they'll train on the censored data. So it could train on sparsely censored data D, which is pairs of the spatial temporal points with the corresponding solution value. And it can go from a coarse grid to a fine interpolation grid. So we just assume that it outputs mean and covariance estimates. As I said, examples of this model could be a Gaussian process or AMP. You could even think of it being an ensemble of neural network type models, anything where we can estimate the mean and covariance. In particular, for future work, we're interested in looking at ensembles of neural operator methods here. And step 2 is where we impose the constraint. We're going to calculate U tilde and sigma tilde according to equation 2, which is performing a Bayesian update. And the main idea here is that we do an oblique projection. What we want to do is utilize the variance information from the black box model. In particular, by doing this oblique projection rather than an orthogonal projection, we're able to update the mean at the precise areas where the black box model is most uncertain, which will show works well on data with heteroscedasticities and in practical problems with shock. So this variance information is quite important, we show to utilize. And in our theorem, we show that we can set sigma g equal to 0 to satisfy the constraint exactly. If you do that, you'll see you have a least squares solution. As another sanity check, let's assume that the initial black box model satisfies the constraint exactly, then g mu is equal to b. And what you get is that we're not changing the mean. Then we set mu tilde equal to the initial black box mean. So as I said, we also provide theoretical guarantees on what happens as we take the noise and the constraint to 0. So the first item that we prove in the appendix is that this sequence converges to the limit monotonically. So we show that the mean will converge in terms of the positive definite inverse covariance matrix monotonically. So we want to make sure that there's no double descent property happening here. In particular, this limiting mean is the solution to a constrained least squares problem that you see defined here, constrained to satisfy the conservation constraint. And importantly, the sequence converges it to be exactly an L2. So we see that we do get exact conservation. And then lastly, if the conservation constraint holds exactly for the true solution, then the distance between the true solution and mean decreases as we take sigma to 0. And lastly, which is important that we show in the empirical evaluation, is that for significantly small sigma g, the log likelihood increases monotonically as we take sigma g to 0. So we do have improved performance in terms of the predictive log likelihood as we take the constraint to 0. And this is just a schematic of our proposed framework, ProbConserve, with using the attentive neural process as the black box model in step 1, which we do in the empirical evaluation. So to review, if we take the attentive neural process, we're trying to learn the parameters theta. It takes this corresponding data as input on, for example, it can be a sparse grid of the spatial temporal pairs, pi, xi, with the corresponding solution. Then you input the output grid that you desire the solution at. The black box model is going to give us our initial estimate for the mean and covariance matrix. And then in step 2, we apply our probabilistic constraint of using the integral form as a Bayesian update as a type of corrector step to output the final mean and covariance estimate. And then we also show the model training that you can justify this 2-step framework as follows. So if we look at the loss function, which is the expectation of the log of the probability distribution P, we can actually perform Bayes' rule here, which will give us, breaking it into these 2 terms, B given U times P of theta times U given D. And then the product of the log is given by the summation, which gives us this 2-step framework here, where what we see is that the step 1 parameter from the AMP or from the black box model is actually only present in the first term in the summation, meaning that its optimal value can be given by breaking this up into the corresponding 2 steps. Now I'd like to go to the evaluation criteria and look at the results of the model. So the 4 things that we try to evaluate here are this integral versus differentiable form. What do we gain by enforcing the constraint using the integral form versus the commonly used differentiable form in scientific machine learning? And then second, the strong control on the conservation constraint as what happens empirically, as we saw in the theorem, as we take the noise to 0. And then point 3, the easy to hard PDE. So this is using our GPME parameterized family of equations to show how and provide better understanding these benchmarks and our model performs, ranging in the easy to hard case. And then lastly, uncertainty quantification for downstream tasks. So the baselines that we consider, as I said, we use the unconstrained attentive neural process. This tries to optimize the evidence lower bound, or the ELBO, which is given by this following expression. So Q theta is the variational distribution of the data used for training, and P theta is our generative model, where Z is the global latent representation. We also propose the following baselines from SciML. So soft CAMP is going to be basically applying pins. So if we add the differentiable form to the loss function as a soft constraint here. So F is the differentiable form, and lambda is our penalty weight, which we do provide tuning on as well. And the third baseline we consider is hard CAMP. So this is saying, what if we hard constrain the constraint to satisfy conservation exactly, but we ignore the variance information? And particularly, this is the expression from our equation, if we set the covariance matrix equal to the identity and the noise equal to 0, which will show can work well on simple problems with homoscedasticity, but not on the problems with shocks and heteroscedasticity, where using the covariance information is actually quite important. So to evaluate the strong control on the conservation constraint for the PME here, what we show is, as we expected, as we take the precision, which is 1 over the noise, to infinity by taking the noise and the constraint to 0, we see that we satisfy conservation exactly. So CE squared is the norm of the conservation error. Now let's look at what happens to the predictive log likelihood metric. We see that as we take the precision to infinity, the log likelihood also monotonically increases, as we proved in the theorem. We also look at the mean squared error, which is a bit more interesting. So here we're looking at the PME, where M is the corresponding exponent from 1, 3 to 6. As we increase the values of M, we see sharper problems that are more difficult to solve. In the heat transfer community, M is typically around 4.5 to 5. And for the coarse medium community, M is taken between 1 to 3, with 1 being the simplest case of Boussinesq approximation. So we see for M is equal to 1, we see that improved performance as we take the constraint noise to 0. However, for M is equal to 3, we do see a U-shaped curve and a sweet spot for non-zero sigma. And in particular, for M is equal to 6, the performance gets worse as we increase the constraint exactly. So this also has to do with numerical issues that are occurring on these sharper problems in our integral discretization, which we show we can improve with better discretization choices there as well. So this is one of the interesting results of the paper. So here we're going to start looking at the diffusion equation, which is the simple constant coefficient case of the heat equation. And what we show is that the unconstrained model violates conservation of mass. The true mass is 0 over time. We have no input flux or output flux to the domain, which you'll see that hard C and our model prob conserve satisfy exactly. And so we have 0 net flux from domain boundaries, but the unconstrained model is oscillatory and violating this conservation of mass. In particular, interesting, if we do add the pins constraint, which is shown in green, it does not resolve the issue. We still have an oscillatory profile, showing that the soft constraint format is not sufficient here, even on a simple problem. And now let's look at the solution profiles with the corresponding uncertainty quantification, which are important for interpretability. What we see on this easy problem is that the uncertainty is relatively homoscedastic, meaning that it's approximately equal everywhere. We see that here, the hard C model actually performs quite well, where the constant variance assumption approximately holds. So in this table, we're showing the conservation error in the first column, the predictive log likelihood, as well as the MSE. And this is the mean and variance reported over 50 runs, where we train on the diffusivity parameter in the range 1 to 5, and at test time predict at k is equal to 1 for this parameter. And we'll see the hard C baseline, as I said, performing well here. So now let's look at more challenging cases. This is our medium PME problem. In the first row, you'll see m is equal to 1, m is equal to 3, and m is equal to 6. So there's a big difference even in the solution behavior from m is equal to 1 to higher powers. In particular, here we're starting to see the uncertainty be heteroscedastic, as you would expect. It's largest as this degenerate point, or the point with largest gradient at the sharp corner transition, as we would expect. And here we train on values of m from 1 to 6. In particular, if we apply diffusion to our scheme, we're able to minimize the uncertainty region that goes negative. Here, the solution, which represents density, should be positive, and improve the performance there as well. If you look at the error profiles, the largest error is exactly at the degeneracy region, as you would expect. And here are the corresponding results here, with ProbConserve, especially with diffusion added, performing the strongest. And lastly, we look at the hard case of the Stefan problem. Here we're looking at conservation of mass curve again, so the integral of u over t. By design, our model and hard C conserve mass exactly. So we do use the numerically stable limiting solution with sigma g equals 0, the result. Again, what we see is that the unconstrained A and P, as well as the soft constrained pin solution, have incorrect solution profiles for the conservation of mass. In particular, they're predicting a linear profile with adding the soft constraint is not improving. And it's missing the square root of t. Now, this is even more challenging case than the PME, because in the PME, you can show that that degeneracy point x happens at exactly x is equal to t, where here it's going to depend on the parameter u star, independent of m in the prior example. So we do see the mass being violated here quite significantly. And if we look at the corresponding solution, shown as the dotted black line here, we'll see that this is the problem with a corresponding shock representing two-phase flow. And for ProbConserve, we significantly are able to more sharply capture this shock. You'll see that it's quite diffusive in the unconstrained model. Another thing to note is that this is a problem that's highly heteroscedastic, where we have the largest uncertainty at the corresponding shock location. And in particular, by hard C using the constant variance assumption and ignoring this change in variance, where it's very confident in the zero degenerate region, but has large uncertainty here. It's actually adding bias and making the confidence interval larger in the confident region and not improving the performance at the shock location as our model does. Perhaps more convincingly is to look at the corresponding downstream task. So here we use this to do the downstream task of shock location detection. Here I'm plotting the posterior of the shock position, with the shock position shown as the vertical black line here. And what we see is that ProbConserve actually moves this distribution with its mode at this exact shock location. And so it's performing better at the downstream task as well.
And lastly, we see this in the corresponding error metrics, where we have a 3 times decrease in MSE here for our model. So with that, I'd like to go to the last physical constraint we look at, which is enforcing boundary conditions in data-driven neural operator solutions to PDEs. We'll first review neural operators in more detail. So first, let's look at this motivating example, which is why do we need physical constraints? As we saw, there was motivation for satisfying conservation exactly for resulting in a physical solution that doesn't violate physical laws, as well as improved accuracy of the model. And we'll see the same thing here with boundary conditions. So here we consider a simple heat equation that we saw earlier with these corresponding Neumann boundary conditions. At the left boundary, we have an insulator, which means that the derivative should be equal to 0 across this boundary. And at the right, we have a heater flux, which means that the derivative or Neumann boundary condition should be positive across this boundary. And what we see is that the left is the Fourier neural operator shown in green actually violates and allows heat flux through an insulator. In particular, at this boundary, it has a positive heat flux through an insulator. Whereas our proposed Boone method, which I'll go into next, satisfies the boundary condition exactly. What we show more surprisingly is that it also helps guide the learning process, where it gives smaller area on the interior of the domain as well. And similarly on the right, we do see violation of heat flux with the Fourier neural operator at this boundary, giving a negative heat flux across a heater. So this is the motivating example, as I said, in our recent iClear submission with our PhD student intern Nadeem Saad, coworkers Ashima Aziadad, Gaurav Gupta, which we looked at guiding continuous operator learning through physics-based boundary conditions. So reviewing the boundary value problem, it's similar to what we saw in the ProbConserve problem definition. And we still have our corresponding PDE with initial condition. And here we'll assume we have a linear boundary condition. So now our constraint MathCalG is going to be given by this linear boundary condition. And in particular, boundary conditions are inherent parts of the problem definition, which are readily available and can be used carefully to make inference accurate by orders of magnitude, which we'll show in the results. So here's an example of the boundary conditions that we consider in this paper, which are canonical boundary conditions commonly used in PDEs that carry different physical meanings. The first is Dirichlet boundary condition, which fixes the solution to be alpha d, some time varying function at the particular boundary. And then Neumann boundary condition is fixing, this is what we saw in the motivating example, the derivative value at the boundary. And then lastly, periodic boundary condition is fixing the two values to be equal to each other at the boundary condition. So as I said, here's a review of neural operators. Here we're aiming to learn the mapping between two function spaces, where A is our input space that can consist of the initial condition or PD parameters to the output space U. So it's learning the map between these two function spaces. An example is the corresponding integral operator where we multiply T times A of X. And what's commonly done is you can write this as a convolution with a kernel function K of XY convolved with the initial state. Examples of these kernel-based methods are the Fourier neural operator by Lee et al., as well as the multi-wavelet-based neural operator by Gupta et al. What we show in this work is that unconstrained neural operators do not obey boundary conditions strictly, and they can be moved by careful modifications, again, by incorporating numerics. So what do we mean by boundary constrained neural operators? We propose this boundary enforcing operator net or Boole model here. And the idea here is that we want to find the operator T tilde such that the boundary error is 0. So even if, which is an interesting finding in both of these works, the boundary condition is satisfied in the training data through the simulation data, we find that there's no guarantee at inference, as we saw in the motivating example, that the constraint will be satisfied. So we want to modify this operator to take it such that this epsilon boundary term goes to 0. And we define epsilon boundary to be the corresponding subleft norm of the boundary condition applied to the learned operator minus that of the true operator P. The key intuition here is that we know the initial state A of Y is input that satisfies some constraint. The idea is to define the kernel K of XY to manipulate this kernel to propagate the constraint, such that the output U of XT satisfies the constraint. And we do this via simple kernel manipulation. Again, taking techniques from numerical linear algebra, we first apply Gaussian elimination and then normalization here to the corresponding kernel. Here we show this pictorially via matrices, and we'll see on the next slide that you don't have to explicitly form the matrix for computational efficiency. So what we do is we form these elementary matrices T and multiply on the left and right by K. So for the Dirichlet boundary condition, we're trying to extract the corresponding first element of K by multiplying on the left and right by these elementary matrices. For Neumann, it's the same Gaussian elimination, except we do have these values which represent the corresponding coefficients in the finite difference discretization of the derivative. And lastly, for periodic, we apply a weighted averaging of the first and last element, where the first row and last row correspond to the boundaries. And we show that this model also works and extends in higher dimensions. So you can also propose a computationally efficient approach. We do not need to form the matrix exactly. In particular, all we need access to is some module MathCalK, which can compute matrix vector multiplications. And what's nice about this method is we can take any unconstrained neural operator. So K could be the Fourier basis for FNO or the multi-wavelet basis for MWT as well. We take the initial condition as well as the corresponding boundary condition. And you'll see that the algorithms for Dirichlet and Neumann are almost identical. We first perform the Gaussian elimination. So this is extracting the first element in the first column and first row of K by multiplying this matrix vector multiplication by the elementary vector E0. And then we compute Z as follows. And this is our Gaussian elimination step here. Once we have U0, we set it equal to the corresponding boundary condition as a hard constraint. Similar procedure for Neumann, where I said we do have this finite difference stencil here as well. And lastly, for periodic, we just extend it as a weighted linear combination and then set these two values equal to each other. In terms of the computational complexity, given a grid resolution n, our kernel procedure takes at most only 3 kernel calls of this matrix vector multiplication, which requires order nk operations. So we have the same complexity as the unconstrained neural operators and order n in space. And this is just a schematic of the Boone architecture. You'll see it's quite similar to standard neural operator architecture, where we have our input A, which is going through a MLP to do the upscaling. And then we'll have these layers of K boundary followed by the nonlinear activation function. And then lastly, a fully connected network to downscale to give the final solution. What we show in the schematic for the 3 boundary conditions that we consider, this is taking the algorithm, each number is the corresponding line of the algorithm. So for Dirichlet, we're first multiplying K by the elementary vector E0 to get K0, 0. Then we multiply it by U, perform the Gaussian elimination, and fix the boundary value. And Neumann is quite similar. We'll see periodic is only done in the corresponding 3 steps here. So with that, let's move to the results of this as well. So here we do a quite large benchmarking study on a range of PDEs. We first look at Stokes' second problem with the Dirichlet boundary condition. And you'll see our proposed Boone model in the first row here as time is moving to the right, and we'll have FNO below. What's interesting to note here is that the boundary error is larger, which is denoted by darker red color for FNO as expected than our model. However, this propagates forward in the interior of the domain, with FNO having significant larger error on the interior than our proposed model, showing that satisfying the boundary condition also improves the interior accuracy and the learning procedure. If we zoom in here, we see what's happening is that FNO is actually overshooting the boundary, which is hurting the interior accuracy. So we're not matching the solution profile exactly with the unconstrained model, which is corrected with our Boone proposed model. And we see the corresponding results in the table. So here we test on various viscosity values ranging from 0.1 to 0.1 and show that our model performs the strongest on the multi-step prediction for M is equal to 25 on a resolution of N equals 500 grid points. We compare to FNO as well as the physically informed neural operator, which is adding the pins loss to the loss function. We actually had a hard time, similar to the characterizing failure modes of neural physics informed neural networks paper by Krishnapov and Michael Mahoney's group at NeurIPS 2021. We saw similar issues here with Pinot sometimes being harder to train than FNO due to the challenges in the loss function. What they show in that paper is adding the constraint, the PDE, which could be non-convex and nonlinear, can create a loss landscape that is highly non-convex and sharp and harder to optimize, as well as increasing the condition number. And we also compare to DeepONet here, which has significantly higher error. So you'll see reported in this table is the L2 error over the entire domain, and in parentheses, the L2 boundary error. Next, we test Amberger's equation with shock, so a more challenging setup than's been shown in the literature, and we use a Dirichlet boundary condition. We see that Boone, given by the red curve here, has approximately constant error, regardless of where it is on the domain. But we see that FNO has larger error on the interior, and it grows exponentially as the shock crosses that right boundary at x is equal to 1. And we'll see the corresponding results here that actually lead to a 4 to 30 times improvement in accuracy. So this is Berger's single step prediction for N equals 500 grid points with various viscosity, viscous Berger. So as we take the viscosity parameter 0, the solution becomes sharper and sharper. And we see large improvements here. As I said, we also test Amberger's with periodic boundary conditions where they're using a Gaussian initial condition, which is a smoother setup, and we show stronger performance here as well for various grid resolutions. Also showing good performance even on a coarse mesh of 32 points. And we show 2D examples. So this is the 2D Navier-Stokes equation using lid-driven cavity flow, where the whole flow is actually driven by the non-zero boundary condition at this top boundary here. We show that we qualitatively match the ground truth, as well as has significantly lower relative L2 error over time, where Boone is shown in blue here. And then we also plot the relative L2 error as a function of the Reynolds number. So as the Reynolds number is increasing, we have more turbulent flow. And you can see there's actually significant boundary error by FNO and PINO here as well. And we also look at the 2D wave equation with Neumann boundary condition at various grid resolutions. And what you see about neural operators, which is interesting, especially comparing to numerical methods, is this resolution independence property that the error is approximately constant as you increase the grid resolution. Whereas for numerical methods, the error will tend to zero as we increase the resolution. And lastly, we look at the heat equation with Neumann boundary condition, which was our motivating example. And so even on the simple case, for example, PINO is, even with hyperparameter tuning, a bit more unstable than FNO and having quite large boundary error, as well as with deep ONet, which is significantly hurting the performance on the interior of the domain as well. And the last thing I want to note for the heat equation with Neumann boundary condition is this resolution invariance property. So Boone still respects the resolution invariance property of neural operators, which is important in practice, meaning that we can train on a coarse mesh of 256 points and even provide inference up to a very fine mesh of 4,096 points with about constant error. So to conclude, I wanted to show today that advanced numerical methods need to be incorporated within deep learning models to effectively model continuous dynamics in scientific applications and deal with distribution shifts as well. The first example we looked at was AutoODE, where we incorporate the Runge-Kutta RK4 fourth order discretization. We discretize the SUEIR ODEs from epidemiology with RK4 to be able to incorporate this domain knowledge and better handle distribution shift in learning dynamical systems than pure black box models. Then we look at the integral form in our ProbConserve paper, which provides a framework for enforcing conservation laws within black box probabilistic machine learning models by incorporating the integral form from finite volume methods. It outputs uncertainty quantification and performs well with shocks and heteroscedasticities, as well as downstream tasks of practical importance, such as shock location detection. And lastly, we look at boundary conditions. Our Boone model hard constrains neural operator solutions to PDEs to result in zero boundary error and better guide the learning process on the interior domain, resulting in higher accuracy by orders of magnitude. And here are the main references from today's talk as well. The first is our AutoODE paper, which was published in L4DC, the two numerical papers in JCP, as well as our recent paper with our PhD student intern, Derek Hansen, Shima Aziadad, Gaurav Gupta, as well as Amazon scholar Michael Mahoney, which is archive preprint link here and currently under review, and then our corresponding iCare paper. And we also have the open source code if anyone's interested in running these simulations as well. Within GlueNTS, AutoODE is in the GlueNTS nursery, and we have ProbConserve and Boone on the Amazon Science repo as well. And with that, thank you very much for having me again. It was so nice to be here. I've included my email if you have any questions, as well as I can discuss now, and website for more information on the papers.
Yeah, thank you very much. Thank you. Thanks.
Thank you.
Any questions? Any questions or comments?
Yeah, I have a curiosity question. It looks like you used a lot of physics examples.
Yes.
In a very beautiful way.
Thank you.
And you also that shed lots of light on explainability of the black box,
Right.
which is a big merit of your work.
Thank
and
you.
The question to be, you have touched at the beginning about the COVID with a lot of uncertainties there. Most models basically fail, and
Right.
they admit so. And my question would be, the explainability, is it very hard to translate to social situations which are much more difficult to model than the constrained full control physics or physical experiments.
Yeah, I think that's a great question. So even trying to model maybe the social behavior during COVID, for instance, which may not be governed by these type of equations. We haven't tried that, but I think that would definitely be interesting for future work as well, which may be more on the machine learning side.
So like the agent-based models or
Exactly, like an agent-based maybe reinforcement learning.
reinforcement learning,
Mhm.
trying to give attributes to the subject or to the agent, to the particle, which happens to be a person, no offense, and community, which is an assembly of those agents, and to predict their behavior, as you say, is very difficult, but could it be to make extrapolation from the exact sciences approach, aiming at explainability and better predictability in the social, even political, even global population problems?
Yes, I think that would be really great. And that would be a way, I think, where we could use reinforcement learning here to combine it within these type of models. Yeah, looking at more of the, not, like you said, sciences such as physics, and looking at the social sciences or political to model people's behaviors. Yes, I think that'd be really interesting.
Okay, thank you.
Great, thank you.
A quick question. Thank you for the wonderful talk. My question is from where you talked about using the integral form of
Yes.
dynamical systems. And I know like a lot of machine learning and deep learning packages mostly, are more familiar with the derivatives. So
Right.
do you have to implement your own way of maybe doing quadrature to perform integrals in order to do some of the simulations?
Yeah, that's a really good question. So we did implement basically quadrature rules to compute the integral here. So you can simply use the Riemann sum. If you use more advanced schemes, midpoint or trapezoidal, we also added a scheme with artificial diffusion for the shock problems. You do see improved accuracy. So it does rely on how we discretize the integral. But for future work, we also want to add in local conservation, which is an advantage of finite volume methods, where there they actually assume in the control volume, you can do a first order approximation that with a fine enough grid, the solution is constant there. And if you have a constant function, that will eliminate the integral. So I think local conservation is one of our directions of future work, as well as combining using neural operators as the black box model in step one. So adding a uncertainty estimation there. But yeah, that's a great question.
Okay, thank you.
Thank you.
I have a question. So first of all, thank you for the talk. It was really nice with them.
Thank you.
So my questions concern the first part of the talk about the auto ODE, and I was wondering how big are the time horizons for the forecastings? Because you mentioned that you were preferring the discretized and optimized approach.
Mhm.
And I was wondering, like, how do you tackle the memory requirements? Because like if your time horizons are really big, then you need lots of memory to store all those operations and compute the derivatives. Is that even a problem for you, and how do you handle that?
Yeah, that's a great question. So for the COVID-19, we were doing the 7 days, so weekly forecasts ahead, which was typically done then. And basically, one advantage of us discretizing first, this discretize then optimize, is we're not really relying on auto diff exactly for calculating those derivatives. And since we've done the discretization first and then propagate that through the network. So we didn't run into any memory issues there. There was surprising findings doing the COVID-19 forecasting, especially trying to apply the probabilistic deep learning models there. We also found that it performed better with a shorter context length, so less time points in the past in the model, where typically we found including longer histories would perform better. But due to the very frequent distribution shift, as I mentioned, due to policy changes, which connects to the social future work here as well, we found actually using a smaller number of points perform better. So we didn't run into memory issues there. But yeah, I think that's a great question and a great thing to consider. But we did and compare to NeuralODE and find significantly better performance with the simpler AutoODE, at least in the COVID example. Go back to that table here.
Yeah. Yeah. Thank you very much. Yeah.
Great, thank you.
Other questions or comments? All right, similar. Yeah, thank you very much again for the nice seminar, and looking forward to seeing you again. Thank you very much.
Great, thank you so much for having me.
Yeah, thank you. Thanks, bye-bye.